It's the last 2 seconds of the Tour de France, and the winner is Timmy Velocity. After beginning his research, Timmy realizes that there are so many factors that need to be considered, but the concept of drag was a major issue to many cyclists. So let's figure out what drag is and its effect on cycling. Before we get started, let's define drag. There are many types of drag, but the main type we are concerned with is form drag. This type of drag occurs when molecules of a fluid, which is a movable medium that includes air, collides with an object such as a cyclist and as a result takes energy away from it. Essentially, these collisions will decrease the velocity of an object. The formula used to calculate drag is as follows. F equals 1/2 times D times P times A times V squared, where F is the drag force, D is the coefficient of drag, P is the density of the fluid, in which in our case is air, A is the frontal surface area of the cyclist, and V squared is the cyclist's velocity with respect to the wind. Since Timmy is aiming to increase his speed, he needs to be able to reduce the drag by manipulating the drag coefficient, or the shape of the object, as well as the frontal surface area. Now let's consider how frontal surface area and varying cycling positions affect drag force. The 3 positions commonly used include the Hood's position, the drop position, and the tri-bar position. Let us first begin by looking at the Hood's position, which has the highest frontal surface area. As we can see here, the model is positioned erect with hands placed right above the bar. This position is commonly used for comfort and climbing, but is not ideal for greater speeds. The surface area of this position was calculated as 0.3552 meters squared through software commonly used for bike fittings. By using predetermined values for drag coefficient, velocity, and density of air at sea level, the drag force of this position can be calculated as follows. As we can see, the drag forces required of the biker at this position is approximately 118.34 newtons. Next, the drop position, where hand grip is on the lowest portion of the handle. The cyclist's torso is lowered and the elbows are tucked close to the body. Essentially, its main purpose is for descending control and is more aerodynamic than that of the Hood's position. The surface area for this form was calculated as 0.34 meters squared using the same software. Accordingly, the drag forces of the drop position was calculated as 104.14 newtons, which is a decrease in the amount of drag resisting the cyclist. The trial bars, also known as aero bars, are commonly used during time trial races, where forearms are placed at the center of the front handles in a triangular position. This reduces air resistance dramatically, as the cyclist is also stooped down and leaned forward. The pointed edge of the triangular shape created by the hands of the cyclist causes a decreased rate of collisions at a higher angle of incidence. Therefore, less energy is lost between the object and the fluid. The frontal surface area is decreased to 0.28 meters squared in this position, thereby making this position even more aerodynamic than the previous 2. Lastly, a calculation of 82.38 newtons was obtained for the tri-bar position, representing a significant decrease in drag force, thus supporting that this is the most aerodynamic position due to the decreased surface area. Another type of drag that cyclists must consider is known as surface drag. Surface drag is affected by the roughness of surfaces such as our skin or clothing. As fluids make contact with the cyclist and the bike, small pockets or ridges in our skin and clothing catch the fluids, and thus energy is transferred yet again. Essentially, this is friction force, which is why surface drag is also referred to as friction drag. It is suggested that wearing non-porous synthetic materials allows fluids to travel more smoothly over the surface as opposed to natural fabrics, such as cotton, which tends to create more friction as the fluids are likely to get caught. Form drag accounts for most of the drag force at faster velocities, whereas surface drag accounts for most of the drag force at slower velocities. Other things Timmy should consider include the helmet type used, his water bottle placement, design of his bike, as well as the hairiness of his body. So in summary, we have concluded that drag forces are affected by
the coefficient of drag determined by the shape of the object, air density, frontal surface area, and velocity of the object, which is represented by the formula F equals 1/2 times d times p times a times v squared. Frontal surface area and the shape of the object can be manipulated by varying cycling positions, which include the hoods, drops, and tri-bar positions. Ultimately, the tri-bar position with the lowest frontal surface area proved to be the most aerodynamic. Surface drag should also be considered which encompasses clothing material, bike design, water bottle placement, helmet type, as well as body hair. Lastly, this principle can be applied to other various sports such as luggers, drag racers, divers, and swimmers, a function of hydrodynamics that we have not covered.